Okay, so this is the first chapter of Year 2 Stats, Regression, Correlation, and Hypothesis Tests. Pretty nice chapter, this one. Starts off as a recap, mostly of Pure. We're going to talk about something called PMCC, which really sort of gives you the gradient. Yeah, sort of gives you a number, if you like, that describes a line of best fit. So that number tells you what the diagram would look like. And then there is a hypothesis testing that we can do for this situation. So the entry ticket here is just testing your basic log skills. So a big focus of this chapter is about something called regression. Regression is the idea, can you take some data here and can you make it into a straight line? And it seems like quite a basic thing to do. You've done it by hand. We're going to do it a little bit more robustly. Why would you do this though? Well, you would do this because you could then use this line, couldn't you, in the future? If somebody said, "Oh, I spent this much time revising. Oh, this might be my mark." Um, you could even, so you can use it to predict. You could sort of go to these values here, but then you are extrapolating, you're sort of going outside the data that you collected. So it might be less effective, but the idea that we could use it to predict is incredibly useful and powerful, even if it does seem like a fairly simple idea. Depending on the data you get, though, a straight line might not always be the best fit. Straight line was chapter 4 in the first year. That's when this was discussed. So if you had a population, what you might find is instead of a straight line like this, it might be much better to use an equation in this form. And that's not that surprising because what does this part do? Well, that gives you an exponential graph. A just means some number on the front, so it sort of controls where you start. And yeah, you might find that this much better describes your situation and again could be used for prediction. And it's a very simple thing, but if you can make a computer, if you can get it to find an equation that matches a real world situation, that has an enormous number of practical applications in the real world. So if it were an exponential line, how would you go about sort of working with this? Well, you've dealt with this before. Remember that you took logs of this. We went through this process, and this is the way I advise you to go through it so you know what you're doing. But we can go through this process here, and we can sort of turn these values and turn these graphs themselves into straight lines. So instead of working with something like this, which will increase very, very rapidly and quickly, you can turn this situation, so you can describe it first with an exponential, which gives you a very good line of best fit, and then you can turn it into a straight line, which makes it easier to work things out and to look at and to understand and so on. So this would be the initial graph, and then as we saw, if we take log of this value here, not of time staying the same here, if you take log, then you generate this straight line. And in this case, because we took logs of an exponential graph, we end up with this format. This is the format where x remains unchanged. A polynomial would have log of x. So for my turn, let's have a look at the example. So the table shows some data collected on the temperature in a colony, which is T, and its growth rate, which is G. So we've got T and G here. Okay, so what have we got going on? So as temperature is going up, it seems that the growth rate is going up. Let's keep reading. So the data are coded using the changes of variable x equals t. So x and t are sort of the same thing. So this is t, or it is x, and y equals log g. Okay, so let's have a think about what we might need to do with that in a moment. So what is y? Because I've talked about t and g already. So what is x and y? So the regression line, so what they've done here is that they've tried to draw a line. And the regression line is this. So y equals minus 0.22 plus. So it's got a got like a weak positive gradient, and it starts from sort of below the y-axis. So that's what's going on. Okay, so Mika says that the constant, so this number here means that the colony is shrinking when the temperature is 0 degrees. So when T equals 0. explain why she's wrong. So what we need to do really is we need to connect together what's going on. So what we got, y equals log g. Y equals log g. So if I write in here log g instead of y equals, and I write this again, what does this give me? Minus 0.2215. X and t are the same thing. So if we change x to t, we could do that. And it says the temperature is 0. So in other words, that whole part there will disappear. So log g equals this. And this is just being careful and trying to connect the t and g stuff with this equation that's been given to me. They give me this equation, they're talking about this number, so it makes sense that I use it. Now, log g equals this. Well, if we did 10 to the power of on both sides, that would undo the log part, and we'd find it value for g. And this is 10 to a power. Now, that power might be negative, but if you take a positive number, if you take 10 to this power here, you're always going to get a positive number. And G is identified as the growth rate. So the growth rate should actually be a positive number. And you can put that one in your calculator and work it out. So let's take a look. 10 to the power of minus 0.2215. And that gives you a positive number. So little conclusion as well, that the growth rate is positive. Okay. Given that the data can be modeled, so in this equation here, where k and b are constants, find the values of k and b. So think back to your year 1 pure, chapter 14, and what we said is start with these and apply the logs to both sides. So we do log g equals, and then we can work through these steps here. So hopefully you're okay with me sort of jumping ahead a little bit and saying this will be log k plus log b to the power of t, and you can break that up. So log k plus t log b. And then what we do, hopefully this is revision, is we sort of map them to each other. So that is the format of a straight line. Log k is just a number, so that must be the part that is the intercept. So that's that part there. T is a variable, t changes. So t is like the gradient. And log b is a number. So that must be the 0.0792. Okay. What do we actually have to do now? Well, we match them up. So we say that log k is this number. Notice that's exactly what we did over here. So you're going to get the same answer. You're going to get 0.6 for k. And this bit here, so the log b part must be the same as the number part. So if you do 10 to the power of this, you will get the value for b as well. So that's revision really of your year 1, chapter 14 log graph stuff. If this is unclear, as a matter of priority, you need to go and revisit it, because these questions always come up in the papers, and they look more or less like this every time. So finally, we get this number and we get this number here, and we could actually write it out. G equals, so k was 0.600 times b. B is 1.20 to the power of t. And then a typical part C would ask you to actually use that equation there. Part D might ask about limitations, and that's what an exam question sort of would do. Okay, so have a go at your turn here. Just start reading it carefully. It's quite similar to the one before. And I'll put in V here just to add a little bit more to the diagram. So pause the video and have a go. And if we take a look, something very similar should be going on here. So you were given the model right at the start this time, and you can break this up and match it. Okay, so that part there is going to be the log k part, so the number to the number. And what are we going to have? The log b part, which will be the coefficient of the t after you break it up. The log b part is going to be the same as the 0.3 part. So you found those two values. We've got another example. So T is the number of years after 2011. So that should be 1 and 2 and 3 and 4 and so on. Again, you've been given your model here. So what you're going to do is you're going to say log V equals log A plus T log B. And what we're going to do, well, this time, because you've actually been given the coordinates, you could actually put all of this into your calculator. If that's V, you need log V, it says. So find log V. So do log of each of these values. And then go on to the stats mode again on the calculator. The stats mode, the Y equals A plus BX mode. And type in the T's, so 1, 2, 3, etc., etc., and then log of each of these values. Okay, and then log of that one, blah, 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 blah. Once you've done all that, press equals, and then the option button, and regression calculation. And then that should tell you your A and your B value, but also it will tell you your R. So let's have a look. Underneath here, then, they've done log. In fact, because of the type of model that it is, if we take a look, this one's going to have log T as well as log V. So you'll actually have to log your T values as well as your V values. So log T and log V, log T and log V. So unfortunately, that's what happens if you don't take the time to apply logs, which we didn't on this part. You can't necessarily always see that. You might miss the fact that it needs to be log T. The calculator, though, will give you your intercept, okay, and it will give you your gradient, and then you do 10 to the power of on both of these parts, or 10 to the power of on the A part. You don't actually need to do 10 to the power of on this part, but then it should complete your model. Okay. So yeah, all of this stuff here, for the drawing aspect, instead of drawing it out yourself and finding the intercept, if you log the values of both, use it on your calculator. It's much easier and much quicker. Okay, and that takes you up to exercise 1A.